Okay, we're going to look at the different stereoisomers you can get when there are two stereocentres in a molecule. Let's start with this molecule. As you can see, there are two stereocentres. A better way to draw this molecule would be something like this. I'm putting the hydrogen to the back so it's easier to assign the stereochemistry R and S. For the first example, I have kept both the hydroxyl groups at the front. I'm going to draw the other molecule with different stereochemistry at one of the stereocentres. I'm keeping both hydrogens at the back of the molecule to make things easier. As you can see, the bromine and the hydroxy group are now pointing forwards in this molecule. From here to here, I've changed one stereocentre, this one. We can also draw each molecule with two different stereocentres changed. I've drawn this as the mirror image to make it more clearer later on. However, you can see if you flip this molecule over, it does not superimpose on this one. Here is a model of this molecule. As you can see, both hydrogens are facing backwards, bromine at the top, two hydroxyl groups, and the carboxyl group. If we flip it this way, you can see actually both hydroxy groups are facing backwards, while the hydrogens are facing forwards. We can do the same for the bottom molecule. As you can see, this is not the same as this for the same reason. Now, let's assign R and S to each of the stereocentres. In the first case, bromine must be number 1 in the case of this stereocentre. Oxygen number 2, and because this is a carbon, that's number 3. Therefore, this is S. For this stereocentre, oxygen is the highest, then it goes carbon, carbon, oxygen, bromine. Bromine wins, this carbon is second, and this is third. This gives R stereochemistry. I'll do the same with the bottom molecule. Oxygen first, 2, 3. This is the same, as this stereocenter hasn't changed, R. However, this one has changed. Bromine is still 1, oxygen is still 2, carbon is still 3. However, it's now R. When put through a mirror plane, as there is, to separate these two molecules, we can just simply invert the stereochemistry. The side with the carboxyl group used to be R, it's now S. And the side with the bromine used to be S, is now R. The same for the bottom molecule, carboxyl group R, S, and the side with the bromine is S. As you can see, two non-equivalent stereocenters has given 4 stereo isomers. As you can see, because they are reflections of each other and they are not superimposable, this pair and this pair are both enantiomers. These two and these two aren't mirror images of each other. They are not enantiomers. However, they have different stereochemistry. We call these diastereoisomers. Therefore, normally we can say that a molecule with n stereocenters will have 2 n stereo isomers. However, this is only true for molecules with non-equivalent stereocenters. Let's have a look at molecules with equivalent stereocenters, so 2 stereocenters that are the same. Instead of a carboxyl group, I'm going to have an extra bromine. So I'll keep both hydrogens at the back to make everything easy. Let's have 2 bromines on the top and 2 hydroxyl groups pointing forwards. In the same way as before, you can see that we can put these into 4 different arrangements, which I'll do now. And we can go ahead and assign R and S to the 2 stereocenters in each molecule. So we'll start with bromine. Bromine is 1, oxygen is 2, carbon is 3. 1, 2, 3. So you can see that one is S. Bromine is 1, oxygen is 2, and carbon is 3. So you can see this one is R. I'll go ahead and do the rest of these quickly. Okay, as you can see, we have a molecule S and R, a molecule with R and S, a molecule with two R's, and a molecule with two S's. So you would think that there are 4 different arrangements which give 4 different stereoisomers. However, look closely. Here I've made the RR model. So you can see hydroxy at the top, bromine at the bottom, and a hydroxy at the bottom as well, with both hydrogens facing backwards. If we try to make this into this model, we find that we can't. There is no possible way of rearranging the atoms to get both hydrogens at the back and a bromine on this side at the top with the hydroxy at the front. However, if we look at this molecule, if we change the stereocenter on the right, we can see 2 bromines at the front, 2 bromines at the front, 2 hydrogens at the back, and the 2 hydroxy groups on the top. To get to this model, we can actually rotate and then flip this way, and it becomes 2 bromines on the top, 2 hydroxy at the front, and both hydrogens at the back. All in all, these molecules are the same. We call this the meso form. Again, we can see that these 2 molecules are enantiomers because they are mirror images of each other. This time we've seen that 2 equivalent stereocentres actually gives only 3 stereoisomers. We can write a new rule for this, which is N equivalent stereocentres will give 2 to the power of n minus 1 stereoisomers. Therefore, in this molecule, we have 2 to the power of 2 minus 1 equals 2 diastereoisomers. We have a pair of enantiomers and a pair of diastereoisomers.